Circuitry. Basically, there are two equations. Yeah, there's a couple of more. I mean, I did start out, so I'm going to write down here, two main equations, okay? We did define current. We said that current was equal to coulombs per second. That's an amp. That's the definition. And you know what? There is going to be one question, one multiple choice question on your test where I have you, where I say something like, how many coulombs of charge come by in 30 seconds? What you really have to do is you have to find the current, and then T is 30, and you can solve for Q. Fair enough. But really, the two main equations we have are V equals I times R. In fact, you know what? They're important enough. I'll differentiate them by typing them. The two main equations, V equals I times R, and power equals V times I. Okay. That second one there has a couple of other versions. If I'm clever enough to plug V equals I times R, you do also get power equals I squared R, and you get power equals V squared over R. That's if you plug that in for the V, you get I squared R. Or if you get the I by itself by dividing by R, and you plug V over R in for the I, you get VV over R. These two will come in handy once or twice on the test. In fact, there is one question where, as a shortcut, if you happen to know this, you can get a lot further, a lot quicker than having to find a whole bunch of other stuff. Okay? There is a third equation. The third equation was terminal voltage, which is the maximum theoretical voltage, what you lose going through the battery. The EMF, that symbol E, is printed on the battery. It's constant. And this is what voltage we lose traveling through the battery. Now on your formula sheet, Jake, it's actually plus or minus. The plus is when you're recharging a battery, and it was pretty obvious there was two batteries facing each other in the circuit. I'm trying to remember. I don't think I asked you to do a rechargeable on this test. So I'm gonna do that, even though on your formula sheet they're both on there, plus or minus. Having said that, Vikas, you notice I really didn't use this. I half the time, if you asked me to find the terminal voltage, I just skied. In fact, really what we need to know is and this is the ski hill analogy, where voltage was the height, the battery was the chairlift, current was the number of skiers, resistance was sort of how deep the snow was, but we didn't really have to go that far. Once we had voltage, once you had current, the question fell apart. Then you could do the rest of it mathematically. What are Kirchhoff's rules for solving circuits? The first one is the current rule. Current into a junction equals current out of a junction. Charge doesn't vanish. Then we had the voltage rule. If you travel in a complete circle, good gosh, always going downhill, you end up at the same height, and I'll put in brackets here, voltage, that you started at. And what we often did was this. If you start at the chairlift, what was the chairlift in the circuit? you should end up at 0. Ground. Start at the top of the chairlift. You know what? If you start at the, I'll even add top of the chairlift, you should end up at 0 at the bottom. Okay. What was our strategy? Our strategy to solve circuits was as follows. Try to find total current. If you have total current, the question falls apart. I'm telling you it does. If you can't find total current, look for anything with 2 pieces of information on it. If there was any resistor that had 2 pieces of information, because if we know 2, we knew 4. We're using power equals V times I and V equals I times R. If that didn't work, then you would try skiing. Didn't work, you would read the circuit as one resistor, which we called R total. How did you rewrite it? This is where we used R in series meant add them up. R in parallel meant reciprocals. So that's kind of everything. Let's start solving some circuits here. Okay? Example. Pause the video for 1 second while I go find a question. So what kids have been asking me about the most is this notion of terminal voltage. Terminal voltage. So here's a question here. It says, what's the terminal voltage in this particular cell? Now this is from an older review that I used to give out. I'm going to just change one number just to make it a whole new question. Instead of, oh, I didn't want to do that, Mr. Dewick. Need to make the diagram just a wee bit smaller. Didn't want to do that. I want to make it smaller. Okay, let's go this way. Sorry guys, this is not there. That's what I was trying to get. So what's the terminal voltage? Instead of an EMF of 4.5 volts, let's make it an EMF, a source voltage of 5.5 volts. And now it's a whole new question. Okay. You ready? What do I look for first? Total current. Did they tell me total current? This question's going to fall apart. Okay. Now I'm going to start using Ohm's law like crazy. I'm going to start to ski. I'm going to start to do as much as I can here. So how many amps right here? 0.8. How many amps right here? How many amps flowing through this 0.63 ohm resistor? Jake, loud and proud. Hang on a second. How many amps do I lose going, how many volts do I lose going through this? Because now I know 2 things. I can tell you how many volts I lose going through that little internal resistor. It's going to be I times R. It's going to be 0.8 times 63 times 0.63, sorry. I lose 0.504 volts. And I'm done. What's the terminal voltage? The terminal voltage is chairlift, take away the bump at the top. How big is the chairlift? Can you read it, Jake? I changed it from 4.5 to, what do I lose going through the battery? 0.504. Okay. The terminal voltage, all it is chairlift minus bump. As numbers, it's 5.5 volts in this question that I've made up. take away the 0.504 that I lose going through the battery. Heck, I can do this in my head. 5.5 take away 0.5 is 5, take away 0.04. I think it's going to be 4.996, I think. Let's double check that. Okay.
Is the funny looking E, that's the imaginary?
That's the EMF, which is the maximum theoretical, I can't call it imaginary, let's call it theoretical voltage. It's just printed on the battery. Okay. Now you had a question. What was your question, or was that the question?
You answered it.
Okay. Now, if they had wanted me, for example, instead of saying find the terminal voltage, if they had said find how many watts of power going through the 10 ohm resistors. The fact that these two are identical, there is a shortcut. The fact that these two are identical, 10 ohms, how many amps go through each of them if you have 0.8 coming in? 0.4, 0.4. That's the only time that I use those shortcuts. I showed you the whole ratio thing because I'm a nerd. I really don't have those memorized. I can solve those, but it's handy to know it splits up. So this would be 0.4 amps. This would be 0.4 amps. 10 times 0.4 is 4 volts. 4 volts. And now I'm worried that I may have made up an illegal question here. Let me see. Yeah, I have a feeling that I wouldn't get 0.8 amps. So let's pretend we didn't bother solving this part down here. This is the problem with making these up. The numbers often don't work. But that's how I would handle this. Okay? Yes, technically I did go V terminal equals EMF minus I times little r, but you'll notice, because I did it by skiing. I said you gain 5.5, you lose 0.504. Done. Done. Let's try another one, maybe one a little better. Well. Okay. Here's a nice one. Says find the value of mystery resistor R2. Okay. Let me get this all on one screen. Okay. Tiny bit. There we go. Find mystery resistor R2. Suggestions.
Try and see if there's little average, which there is after 2.4.
Yep. Okay. Now, until you get good, by the way, and even if you are good on the test, I might even take the 1 second that it takes to remind myself that's how I'm going to move my eyes always, always. By the way, right here, what direction is the current flowing? To the left or to the right? What direction are the electrons flowing? To the right, okay? Conventional current is in the opposite direction of the electrons, but hopefully I've convinced you why it's so much nicer to just pretend the protons move. Why we're so choked. Ben Franklin named the charges wrong. Should have been nice. He should have made the electrons positive, because they're the ones that are... He just didn't know. Okay. 2.4 amps. So, Clay, how many amps in R4?
2.4.
That's going to be how I'm going to break this apart. I got 2.4 amps. That also means I got 24 volts. Okay. Did they tell me the total battery this time, though? Yeah. Okay. Oh. Here's somewhere else I know two things. Right there. In fact, how many amps Vicus went this way? How many amps went this way? 0.6. 0.6, right? Just read this to me. How many amps went this way?
0.6.
How many amps are there in this circuit grand total?
2.4.
So here's my question, folks. How many amps must have gone that way? Now, if you can't do the math in your head, please make sure you use a calculator on the test. In fact, even if you can do the math in your head, on a test, I'd hedge my bets and I'd still use a calculator. So I must have 1.8 amps. Hey, I know how many volts. Can someone go 1.8 times 5, I times R? Anyone?
He did it in his head.
Okay, let's ski. I don't know how high the chairlift is, but if I go this way, I'm going through the one that I know. How many volts do I lose going through here? How many volts do I lose going through here? Did that get me to the bottom? How many volts are coming from the battery? First of all, what will you be doing? How will you calculate it? How will you calculate it? More specific, please. I want the numbers. 20. I can't. Okay, 24 plus 9. So this has got to be 33 volts. So you could solve this way. Or you could realize right here we're splitting up. Here we're meeting up. How many volts do I lose going through this path? How many volts must I lose going through the green path?
9.
Has to be also 9 because we're splitting up and meeting up. How many volts do I lose in R1? Well, R1 is going to be 0.6 times 6. R1 is going to be 3.6 volts. How many volts must I lose in R2? How many volts from here to here?
2.4.
How many volts from here to here?
9.
9. How many volts do I lose here? How many volts must that be? How can I calculate it? Tell me what to type into my calculator.
9 minus 3.6.
Which is what? Okay. Okay. Alex, how many volts? 5.4. How many amps in R2? And I'm done because they want me to calculate R2. Now I'm going back to V equals I times R. Voltage in resistor 2 is current in resistor 2 times resistor 2. How would I get R2 by itself? It's going to be V over I. It's going to be, make sure you use the right numbers. The classic I see here, kids are, they'll go, the voltage 33. No, not in that resistor. The voltage drop in that resistor is 5.4 divided by 0.6,
Should put a little R
which is what?
underneath the V. You know, so then it's like you know you're using it.
Well, really what I should do is
Yeah, there.
which
That's
I
right.
started and I wasn't consistent. Should be 9 ohms, yes? Okay. I would consider that B minus level. What's above a B minus when you have to rewrite the circuit? You'll notice we didn't have to rewrite anything. We were able to just ski and hopscotch our way there. We didn't have to do the 1 over R parallel, 1 over, 1 over. That's when it gets trickier, but funner in many ways in my mind. Let me find a good terminal voltage one. Oh, as a part B, calculate the power dissipated by R2. So on this provincial exam, part 2 was calculate the power. Well, now that you know I, now that you know V, it's going to be 5.4 times 6. That's how many watts is inside there. So that's not a big stretch. Okay. I think this one here, I'm going to have to rewrite. How can I tell at a glance that this one here I'm going to have to rewrite? No amps anywhere. In fact, that really, if they don't give me amps anywhere and nothing with 2, I'm rewriting this sucker. Okay? So this would be considered, yeah, a good fair game question. It says, what's the power dissipated in the 33 ohm resistor below? Click.
Are we gonna find the total resistance?
Probably. But we'll keep our eyes open to see if we can take shortcuts along the way. Just to make this a new question, 16 volts. There, now it's a new question. That I think I'm okay on because there was no current. Okay. Yeah. Current anywhere? No. Skiing? No. Anywhere with 2 things? No. We have to rewrite this. Okay. I'm lazy, but I'm organized. So in my rewriting, I'm going to say something like, okay, which part am I going to have to do some rewriting for? That guy, right? So for now, Colin, I'm going to say, well, if you want me to do my mathematical equivalent, let me give myself a bit more room here. I have 16 volts. I run into 10 ohms. There's a mess, and then I run into 10 ohms. Let's deal with this mess. Common mistakes. I see kids do this. 1 over R parallel is 1 over 100 plus 1 over 10 plus 1 over 33. Why is that wrong? Because it is.
I did rate 10 instead of 100.
I'm doing this one here. Oh, why did I write 10 over? Okay, sorry. I didn't know what you're asking me. Okay, these two are in series. Okay, Vikas, who's not foolishly on his phone in my free time. Okay. Those two are in series, but kids do that one all the time. So instead, it's going to be 1 over R parallel equals 1 over 100 plus, if these two are in series, what can I replace them with? Yeah, a 43 ohm resistor. So I'm going to do that part. That's a shortcut that I think I can do sort of in my head. So on my calculator, it's going to be, and now we're getting good at our reciprocal button, 100 reciprocal plus 43 reciprocal and reciprocal. This isn't going to work out nice. It eventually gets too yucky to make these work out nice.
You just put the -1, you don't have to do the...
You can type 1 divided by 100, but 1 divided by 100 is actually 100 reciprocal button. It's even shorter. And then make sure you take the reciprocal of the answer. And I get a parallel equivalent of 30.069. I'll go 30.07. Did you take the reciprocal of your answer?
I did 100 reciprocal, so like -1.
Yep. Plus 43
-1, and I got
equals
0.03.
equals. And then did you take the reciprocal of the answer?
Oh, do I have to take the x1 again?
Yes. This does not, look up, Clay.
See,
Clay, this is key. We don't have an equation to get R parallel. We have an equation to get 1 over R parallel, and then once we have that answer, we have to take the reciprocal at the end. 30.07? Boy, that's a terrible ohm sign, but I don't care. All right. That's the mathematical equivalent. You can go further than that. Usually, once I get everything in series, because series Colin is just adding them up, I usually get a little sloppy here, and I just say, okay, I now know our total. It's going to be 30.07 plus 10 plus 10, which I can do in my head. It's going to be 50.07 ohms. Go ahead, you okay with that? 10 plus that? Yeah. And I do know the total, 16, that's what's coming from my battery. Okay. Mr. Dewick, what if this was a terminal voltage question? What if you had the bump? We'll tackle one like that in a second. Now this question's going to fall apart. I can find total current. It's going to be total voltage divided by total resistance. It's going to be 16 divided by 50.07. You know, I like to keep stuff on my calculator, so I'm going to add 20. There's my total resistance. 16 divided by this. It would be lovely if this works out to like a nice decimal, and okay, maybe not. I'll write 0.31553. I'll carry 6 sig figs because I'm going to be using my current to find a bunch of other stuff. 0.319553. 0.319553 amps. 0.319553. Let's change colors. 0.319553 amps. 0.319553 amps. And in my mathematically equivalent, 0.319553 amps. How many volts? You're multiplying by 10, Clay. Please tell me you don't need a calculator to multiply it by 10.
3.19553.
So up here, 3.1955, 3.1, oh, always put the units, 1953 volts. Oh, how many volts are we starting with? So it seems to me we can ski that path. Yes? We could go 16, take away 3.19553, take away 3.19553, or could have gone just take away times by 2. 9.6089 volts. Come on. 9.60, what did I say? 89 volts. How many volts must both of those be? Okay. .6089 volts. Okay. Oh, how many amps must this be? No, you can calculate. How many? Do I know two things? No, guess. How can I calculate it? How can I calculate it? Put your calculator down. Just tell me how I can calculate it.
Divided by 2.
Sorry?
Divided
What? What? Jake, hit me up. What?
by 2. V divided by R.
V divided by R. Jake, what is R? 100. Please tell me you don't need a calculator to divide by 100. I think if you divide by 100, don't you just move the decimal place over 2 spots? I think we can safely say the current is 0.09089. Now, Clay should use a calculator on a test because apparently if you divide by 100 and you move it over 2 spots, you get 1 0 because you move the decimal over 2 spots. Why is that so handy? How many amps were there grand total in this thing? That many? Yes? Amps went to the left. How many amps went to the right? Not the same number. Don't do that. How many amps are there grand total? Read it to me, Jake. How many amps are there grand total?
0.319.
Went on the left branch.
0.09.
Whatever's left went to the right. Not the same number. Whatever's left, because it splits up, rejoins, right? So it's going to be, let's see if I can get this. 19553 take away 0.09089. How many amps are going up the right-hand side? 0.223. Hey, we're done. What does this question want me to find? What's the power in here? How many amps are in here? 0.223464. How many ohms are in there? Meant to be really obvious. Just this one. 33. This is where, if I had it at my fingertips, I would use the I squared R. You could now find the voltage. You know I, you know R. You can go V equals I times R, and then you can use power equals VI. But the fact that we're sitting there, I would go squared times, hello, squared times 33. And I would say, oh, 1.65 watts. Let's do this at the bottom. Power in the 33 ohm resistor, did they give it a number? They didn't. Is equal to I squared R is equal to 0.223464, 0.223464 squared times 33, 1.65 watts. That to me is much closer to a B plus or even an A level question. What makes it an A, B plus or an A level question? The numbers work out yucky to boot. I mean, sometimes I'm able to cook the numbers column enough that I can give you, nicer decimals. These are pretty hideous decimals. They're going to happen sometimes. Yeah, that's what I'm saying. On the test, it's too tough to try and make everything work out evenly. Way too tough. Let's do one with terminal voltage again, because that's the most recent topic that we looked at. Again, how can I tell it's a terminal voltage question? Ding, 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 right there. Okay. 5 marks. I think this one's probably going to be pretty easy. You know why? I see total current. I have that confidence. How many amps are right here? How many amps are going through this particular mystery resistor? What's the power? You know what? If I know 2 things, I can know 4 things, and this is going to fall apart, I think. But let's try it. So for terminal resistance, for terminal voltage, you'll notice really all I'm doing is I'm treating that little r like another resistor, but I'm remembering that if they want the terminal voltage, it's going to be this minus that voltage. That's the definition. Okay? Well, 0.4 amps. How many volts? What's the equation that has power and current in it?
Power divided by current equals volts.
Oh, so it's going to be,
V equals VI.
I'll write it here so that you know what the heck we did. Dividing by 0.4, the same as dividing by 0.2, and dividing by 0.2. Okay, 8.75. 8.75 what? Units? Volts. Hey, how many volts high is the chairlift?
9.
9. That's what that EMF means. That's the chairlift. Ready? Ready, ready, ready? How many volts high is the chairlift?
9.
How many do we lose on the ski hill?
8.75.
How many must we lose going through that bump? Has to be. Has to be. Now, we could have pulled out the terminal voltage equation. You back with us? We could have. But you know what? I'm telling you, this has to be 0.25 volts. Oh, and how many amps are going through little r? Too slow. How many amps are going through little r? Gotta be. Knock, knock. I know 2 things. So it says, what's the internal resistance? I probably could have done this using that V term equals EMF minus I times R. You know what? I can get there by skiing. The resistance has got to be the voltage in that resistor divided by the current in that resistor. How many volts do we lose in little r, Jake? How many volts do we lose going through little r? Yeah. How many amps? It's a 0.625 ohm resistor. Okay? If you don't ski, if you do this using the formulas and the equations, it is a 5-mark lengthy question. If you ski, it's almost, really, 5 marks for that? Yeah. How would I give out marks? Oh, give you 1 mark if I saw that you clued in the current was 0.4 right there. 1 mark for that, that's 2. 1 mark for that, that's 3. 1 mark for this, that's 4. 1 mark for the answer. There's a part B. What is part B wanting us to answer? Oh, here's a using principles of physics, right to explain question. Here's a nice example. It says the light bulb is now replaced by a lower resistance, a brighter bulb. The terminal voltage will now be, well, remember, the terminal voltage, the way I remember it, and this is coming out of the equation, Clay, it's what's printed on the battery minus what you lose going through the bump. Okay? When you replace the light bulb, does the side of the battery change magically? This doesn't change. Does the internal resistance of the battery itself change? No, that's baked into the battery as well. What is going to change if you change this is that number. Okay? So the real question we need to ask is, if we change this, does this number go up, go down, or stay the same? And then how does that affect the terminal voltage? So, if you pop the bulb out and you replace it with a lower resistance bulb, what happens to your total resistance compared to this situation? Does it go up, go down, or stay the same? First of all, this resistor and this resistor, series or parallel? They're in series. There's no junctions between them, right? They're in series. Let me ask you again then. This resistor and this resistor, series or parallel? Series. So if I wanted to find total resistance mathematically, how do I do that? Alex. Adam. Okay? So if this number, this resistor got smaller, which is what the question says, what would happen to the total resistance? Bigger, smaller, or stay the same? Okay, so my first argument here is going to be our total decreases. With me? That's what happens when you pop the bulb out, replace it with a lower resistance bulb. I total is the total voltage, what's printed on the side of the battery, divided by our total. So what's going to happen to I total? Is it going to go up, go down, or stay the same if the total resistance gets smaller? Increases. You with me? What's going to happen to the bump if I just got bigger? So I just increased. Little r doesn't change. What happens to that number there? Bigger, smaller, this number right here. If I gets bigger. Colin? Bigger. Okay? Right? With me so far? So I'm going to write this down. Therefore, I times little r increases. So remember, this is constant. This just got bigger. If you have a constant minus a bigger number, what happens to our answer? Bigger, smaller, or stays the same? You guys are way overcomplicating this. So let's suppose this is 6 volts printed on the side of the battery. Originally, when you went I times R, you got 0.5 for 5.5. So 6 minus 0.5 is 5.5. This just got bigger. 6 minus a bigger number. Is this going to be bigger, smaller, or stay the same? This is kind of weird. Lowering the resistance, you might think, oh, I'll get a bigger terminal voltage. Actually, somehow, when you run the numbers, when you lower the resistance, the bump got bigger. And this is where my ski hill analogy finally does break down. The terminal voltage got smaller. Okay? Gives you an idea of some of the using principles of physics sort of questions. And you could also, by the way, have solved for all these numbers and then said, oh, you could actually solve for this resistance, because I know 2 things, yes? And then you could have said, oh, they want the resistance to be smaller. I'll resolve this circuit with half the resistance there. So I got a resistance of 8 ohms. I'll put a 4 ohm one there, and I'll walk through the numbers, and you would find, oh, my terminal voltage got smaller. So you could do it with numbers. I did that one reasoning, but you guys are pretty dead after school right now. Normally the reasoning goes a little better, in theory, is the goal, I hope. Let me try a couple more here. I want to get as many with terminal voltage in because that's what I did at the end, and that kind of contains everything else anyhow. This is number 1, Mr. Dewick, really? What is the power dissipated in the 8 ohm resistor as shown? Are we going to have to rewrite this one?
Yeah.
You guys want to do this one? We can. Yeah? Okay. Let's make it a wee bit tougher. So I'm going to go like this. But just for fun, let's add an internal resistance. So I'm going to make this a little bit smaller. Okay, what's the power? Let's put right here a little 0.2 ohm resistor, and then the question would go d d d d d d d d d d d d d d d d d d d d d. Okay, and let's add a part B. What is the terminal voltage? Okay. First thing it wants us to find is the power dissipated in the 8 ohm resistor. It wants us to find power in, for Clay, come on, power in R4. It wants us to find P4 if you want to go. Okay. You guys agree that I have to rewrite this, so let's rewrite this. I'm going to do this down below here. I think I got room. So I have an 80 volt battery. Right here, what did I say the internal resistor was? 0.2. Then there's a 12 ohm. I'm going in the opposite direction for some reason. Let's go with the current. Going down, 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 and we go here. Here I got a mess, but then once I finish that mess, I've got a 10 ohm resistor, yes? Okay. Let's take care of the mess. Why is this a mess? Parallel. 1 over R parallel equals, what am I going to write? And then when I'm done that, take the reciprocal. And so the fastest way, Clay, that you can possibly type this, Colin, I can't remember if I did this with my block A's or not, or I did this with one block, and I don't think I did it with the other block, is you can actually go 12 reciprocal plus 8 reciprocal equals reciprocal. Because that's really where that reciprocal button comes in so handy. Because, right, think about it, because that's a reciprocal, and I want the answer to be reciprocal too. So reciprocal of each, it equals reciprocal. What's this the same as? A single resistor that is 4.8 ohms. What can you tell me about this resistor, this resistor, this resistor, and this resistor? They are in series. And by an amazing, incredible fluke, as I was making these numbers up, that 0.2 is going to combine so nicely with that 4.8. We're actually going to get a nice answer. I wish I could do that and say that I planned that. Not a chance. Our total is, yes? 12 plus 10. No, that's totally wrong. 27. 27. Which is still not bad. I thought 25 for a second I was going to get. Good gosh. Okay, 27. Our whole goal is always we want to find total current, because then it falls apart. It's going to be V total divided by R total. V total, there's my battery. Thought I was doing well. 2.963 amps. And I'll draw that on my mathematical equivalent. 2.963 amps, 2.963 amps, 2.963 amps, 2.963 amps, and heck, I'll even draw it up here. So I have 2.963 amps, 2.963, gonna make it, Clay? 2.963 amps. Oh, I cannot break this up. Now, this is where, if you were good at the ratios thing, you could use it as a shortcut, because 12 is 4 threes and 8 is 2 threes. Sorry, 12 is, try that again. 12 is 3 fours, 8 is 2 fours. You could say it's going to be in a 3 to 2 ratio. Forget it. The amount of work to do that is going to be about the same as skiing. It's going to be about the same as skiing. Why? I times R. And since R is 10, even Clay, while yawning, can do this in his head. 29.63 volts. I times R, it's going to be 2.963 times 12. 35.556. My little internal resistor, I times R, 2.963 times 0.2. 2.963 times 0.2. Going through the battery, we lose 0.5926. By the way, that tells me part B. The terminal voltage is going to be 80 volts minus what I lose going through the battery. The answer to part B is going to be 79.4 volts. And this is why, again, I'm saying, yes, that little equation that I gave you is nice. Really, if you understand the concept, you don't need the equation. It's a much nicer way to go. Okay? Heck, I'll answer that right here. Well, I'll move that down later. What did I say? 0.5926? .5926 volts. Jake, do I know this voltage? Say yes. Do I know this voltage? Do I know this voltage? I know my chairlift. I can figure out what each one of these has to be. These will both be the same voltage loss because we split up and meet up. So, heck, they wanted us to deal with R4, so let's ski through it. I'm going to go like that. How high do we start? How many volts? 80 minus, I don't know R4, but then if I go minus 29.63 minus 35.556 minus 0.5926, do you know how many volts we must lose going through R4? A typo.
You put 2 negative.
14.2214. V equals 14.2214 volts. Could you find the current? Yeah. Now, here again, if you happen to know that power equals V squared R, you could go this number squared, so not V squared R, V squared over R divided by 8. That's how many watts of power is going through this puppy. But if you wanted to, you have 14.2214. V divided by R, there's the current, 1.777, that many amps. And then you could go I times V, V times I, and you also get 25.2. Here's what I know. I can tell you the answer to part A is, so the power in, what do we say, resistor 4 is going to be 14.2214 squared over 8. And I used V squared over R because I was lazy. Okay? Part B. Well, it was 80 minus what we lost going through the battery. 0.5926. Minus 0.5926. What did we say it was? 79.4 volts. What if we changed, for example, this resistor right here? Would that change the terminal voltage? Why? Because it would change the total current. This is why I keep saying everything comes out of total current. Okay? In fact, you can make a prediction. If I put a bigger resistor in here, that would increase total resistance. If we increase total resistance, what would that do? If this number got bigger, what would that do to total current?
Make that go bigger as well.
Sorry,
Make it go bigger as well.
which one?
Um,
If this got bigger, what would that do to total current?
so
Smaller, which would make this voltage loss smaller. The little 0.5926 might be a 0.5426, which would make your terminal voltage bigger. Okay. Just going through my notes. What else do I want to try here? Let's try 29, another terminal voltage question apparently. Oh, not that one. Oh, it's 28. I said 29. Please tell me 20. Ah, there we go. It says the cell shown in the diagram supplies 1.8 amps current to resistors. Okay, and what? Oh, sure, this will work. I'll change the numbers again. So let's try one like this. Do a clip. It says find the terminal voltage. The reason this question is a bit tricky is they didn't give me the total height of the chairlift. See, once I get the diagram all on one page, there's an EMF there, but they didn't tell that to me. That's okay. Instead of 1.8 amps, let's make it 2.0 amps. There, whole new question. Why will this question fall apart? How many amps are going through R1? How many amps are going through R1? How many amps are going through R2? How many volts do we lose going through R1? You can do this in your head. I times R? 2 times 2.5? 5? Don't add, we're multiplying. How many volts do we lose going through R2 in your head, Vikas? Thank you. How many volts do we lose going through this stretch grand total? Clay.
13.
How many volts high must this stretch be?
13.
What's the terminal voltage of this battery? Apparently, when I go this minus that, I got 13. I must have, because the chairlift minus the bump has to equal the hills. You okay with that? So in other words, did we use that terminal voltage equation? No, we skied. We skied. We skied. Part B asked, what is the EMF of the cell? Okay. Suggestions?
Use the amperage to find the voltage in the battery. Voltage drop.
In the, not the battery, the resistor, the internal, okay. So how many amps are going through this 0.5?
2.
Vikas, in your head, if there's 2 amps going through little r, how many volts do we lose going through little r in your head, please?
sorry, moving on. Sorry.
I know. That's why I picked on you. How many volts? 2 amps. R is 0.5. I times R in your head. 2 times 0.5 in your head. Half of 2 in your head.
1.5.
Oh my god.
Hold on. I'm completely on this one. Just one.
always
like,
use your
oh,
calculator.
Ah! Ah, I missed.
Look at how many two out of us get scared right now.
Sorry for those of you at home. Ready, Vikas?
Yes.
How many volts do I lose in this hill?
Lose 5.
Remember that. How many volts do I lose in this hill?
8.
Remember that. How many volts do I lose on the little bump?
1.
Remember that. Oh, grand total, how many volts do I lose? The only way that can be is if the chairlift is how high? 14. Did I use the equation? Well, no, I skied. What's the EMF? Okay, has to be. What would happen if I replaced this resistor with a bigger resistor? What would happen to the EMF?
Yeah, increase,
The EMF, it's a trick question.
decrease.
It's a
Stay
trick.
the same.
Vikas, redeem yourself. What?
It would stay the same.
The EMF is what's printed on the side of the battery. When you change the resistor, does the side of the battery suddenly change the print? EMF is constant. It's the maximum theoretical. What would change is your terminal voltage. How? What would change is total current. So this number here wouldn't change, but that amperage would change, which would give you a different loss going through here, which would give you a different terminal voltage. Bigger or smaller, depending on whether I put a bigger or smaller resistor here. Okay? Hopefully it's starting to come together. I hope. Oh yes. There will be, what does MC stand for? Multiple choice question on the correct placement of meters, of voltmeters and ammeters. Something like this. Number 18. I know, but I don't want to do your homework for you. I'm trying to pick questions you haven't seen before. Make it a little smaller, Mr. Duke. There, that'll fit.
Which grade 7 and trying to push some little kids in the lockers.
Too bad Mr. Hazel.
Okay. So here's a circuit. The battery looks like it's there. For some reason, that's kind of vanished over the years. It says, where would you insert a voltmeter and an ammeter to measure the voltage across resistor R and the current through it? Let's do the ammeter first. What would measure the current going through resistor R?
3.
And ammeters are placed in series because you have to force the skiers to go through them. So no, yes, no, yes. Voltmeter is always placed across 2 areas because you're measuring a height. So which of those, 1 or 4, would measure the height, the change in voltage that's
1.
running through resistor R?
1. So 1.
Let's look right here, okay? We split up. Do we meet up? Yeah. So this and this have to be the same height, the same voltage. Is this one resistor down this hill? Is this one resistor down this hill? Both of these will have the same voltage. So you would measure the voltage across mystery resistor R by measuring the voltage across this resistor. They must be identical. Okay. I think the final thing we'll talk about is the using principles of physics right to explain types of questions. I've given you some examples. There could be one for terminal voltage, bigger or smaller if we change the situation, or EMF bigger or smaller. Oh no, EMF doesn't change, it's a constant. The other one, the other classic one is opening and closing a switch. So let me see if I can find one that's got a switch question here. I think I got one. Right here. It says to answer number 22, but it's number 21. Okay? So it says this. In the circuit above, I can get a tiny bit higher, I think. What's the effect on the ammeter and the voltmeter readings when the switch is closed? By the way, that ammeter is measuring total current, is it not? So really, for the ammeter, I'm going to ask, what happens to total current when I close the switch and when I open the switch? And then I think that's what's going to help me figure out what happens to the voltage drop. Now, the voltage drop looks like it's the voltage drop going through the 2 ohm resistor. You can do these algebraically, but did they give me a number here? Did they give me a number here? They give me a number here. You know what? I'm just going to solve the thing. I'm going to solve it open on the left here. If it's open, what that really means is this doesn't exist. I have a 4 and I have a 2. That 4 and that 2, are they in series or in parallel? So what, I think I heard you say it. What's the total resistance? Yeah, I thought I heard somebody murmur 6. So I'm just going to say when it's open, R total is 6 ohms. V total is 6 volts. I'm coming at you, Vikas. What's I total? Well, I total is going to be V total divided by R total. It's going to be 6 divided by 6 in your head, please. Okay?
And you said like 6.
So you ready? When it's open, how many amps right here? How many amps right here? How many volts do I lose right there? Okay? So I'm going to make a little note. When it's open, let's do this. The voltage in the 2 ohm resistor is 2 volts. So open, total current, voltage across resistor 2. Let's close the switch. Now, these two are in parallel. Now, what I have is, let's change colors, Mr. Dewick. 6-volt battery, 4 ohm resistor. How will I combine the 3 and the 2? So it's going to be reciprocal of 3 plus the reciprocal of 2, reciprocal of that. Not too bad an answer. 1.2 ohms. That's the mathematical equivalent when it's closed. Jake, what's our total now?
5.2.
Yes. I'm going to see if I can do the rest intuitively. Here's my question. Did total resistance get bigger or smaller when you close the switch? Compare it to our original. Smaller. So this number got smaller. What's going to happen to total current? When you divide by a smaller number, what happens to your answer? Bigger. Okay, so the first thing I'm going to make a little note. When you close the switch, the ammeter reading increases. That's wrong. That's wrong, because that says current got smaller. No, current goes up. You with me so far? What is the current? Well, now the total current is going to be 6 divided by 5.2. It's going to be 6 divided by 5.2. It's going to be 1.15, blah, 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 blah. And if I want to figure out the voltage drop here, if I go I times mathematically equivalent R, yes? Now I lose 1.38, let's call it 1.4 volts. How many volts was I losing going through here before? Yeah. 2. How many volts when I close the switch do I lose going through there? Which really means, by the way, this is now 3.6. This has gone up, right? Instead of this being 4 volts and 2 volts, this will now be 4.6 volts. It's gone up, but here this has gone down. So the ammeter reading increases, the voltmeter reading. That gives you an idea of a switch question. Okay, there's a bunch of them in the review. Any other questions you want me to go over?